Hello, everyone. Aaron Patzer of Vital coming to you from Auckland, New Zealand. This time I'm in my bee paddock, so hopefully I don't get stung. Continuing our part on algorithms in healthcare, I wanted to talk about handling free text, natural language processing, or NLP as it's sometimes called, and word vectorization, which is kind of a mathematical term, and the state of the art for how you handle free text. First, some context. In hospitals, septic shock or septic infection, it's a really big deal. There's half a dozen startups that I've seen who are trying to do predictive algorithms for sepsis. I've seen a lot of university professors tackle this particular problem, whether it's sepsis or C. diff or some disease state that you're trying to get out ahead of by an hour, 4 hours, 6 hours, a couple of days. You're trying to predict something. What we've found empirically is you need to look at the human observations, the things that your nurses and your doctors are noting about a patient. This patient seems lethargic. They look green. They haven't been responding in a way that they normally would. There's these kind of intuitive, almost social interactions that they're not captured in checkboxes and the things that you find in an EHR form, they're best captured in free text. The problem is they're captured in free text, and unless you read it traditionally, that is inaccessible data from a machine learning predictive standpoint. And so the traditional way to handle free text was what was called bag of words. Basically, every word becomes either a 1 if it's present or a 0 if it's not present in like a machine learning model. And that's the kind of model that I used to build when I was first starting out in algorithms way back when. I used it for mint.com to categorize financial transactions. It's a little lower stakes if you get that wrong. What we do now is we do something called word vectorization. This is going to be a little bit nerdy, so anybody who doesn't have an engineering background, stick with it. It's kind of fun, actually. So what you do is you take the 10 words before the word you're trying to predict. The patient's pain was reduced using ibuprofen, or the patient used acetaminophen to reduce their pain. So the words before an unknown word, or the word that you're training on, and maybe the 10 words after. And so you use the context, the words before and the words after, to predict the unknown word or to predict a representation for the unknown word. You do a lot of number crunching. Sometimes it can take days or months. And what you'll find is kind of remarkable. And so it turns out that the vector representation, and when I say vector, I mean instead of like an entire 10-page document, doctor's note, or nurse's triage description with a variable number of words, you reduce it down to 50 dimensions or 100 dimensions. We'll talk a little bit about that. And the things that point in the same neighborhood. Vectors are just like directions. So all of the things that are NSAIDs, pain medications, acetaminophen, ibuprofen, naproxen, I'm not a doctor, so you'll have to correct me on this. They all kind of point in like this direction, and then maybe cancer drugs point over here, and then a different set of drugs go over here. But what it is it's called an unsupervised classification or clustering algorithm. So things that are literally similar to one another or co-occur in text appear to have similar directions. So it's literally, you're just saying it's in this grouping from a functional standpoint. And it turns out that works a lot better because in your machine learning models, you have, even if it's a 10-page note or a 1-page note or a 2-sentence note, it gets reduced down to just a direction, basically. More specific. Think of GPS coordinates down to the micron level, kind of specific. And that means that your models have this same number of inputs regardless of how complex the text is. And so they're like mathematically equivalent, and you can train on these word vectors. And it turns out that for the sepsis algorithm, we got world's best results. And the reason that we did this is we handled free text. Everyone else is building these models off of categorical data and lab results and that sort of thing. We just took nurses' triage notes that had these human observations. This patient looks lethargic. This patient looks green. And we vectorized the words using something called BioBERT, which is trained on medical text so it can handle it. And just by using that free text, we moved up from, like 85% accurate to like 94, 95% accurate, which in terms of like sheer number of false positives sent to staff has made all the difference in the world. And so you absolutely need to deal with free text. It is not scary. If you do it in the old school way, you'll consider no cancer and cancer to be almost equivalent, which is bad. So you need to use either LLMs, which are like word vectors, I used it again, on steroids, or you need to use something like BioBERT is my recommendation. Ooh, these videos might be getting too nerdy. Let me know in the comments. Thanks.